also if it's in full screen. So my talk today is on early disease detection using spectral data, focusing more on spectral data, but you're going to see why spectral data and also why talking about early disease detection. So maybe my colleagues previously have talked about disease detection in plants, which usually happens with by use of such as features, like we use a mobile phone, we take an image of a plant, and then we do diagnosis. But here we are faced with a challenge to see, for example, why should we detect diseases when the disease symptoms are very, very visible, or we are close to harvesting the plant. So one of the reasons why we introduced this technology, which is spectrometry, which you see there, it's like a real signal. Want to see, can we be able to read features within a plant before we can see the visible features out. So usually when we see, like for cassava, when we see visible features out, and then it means it's also correlated to the plant or the tuber of the crop, that it's already sick or it's already affected somewhere, we cannot consume on it. So this is a new technology which was proposed early when I was starting my PhD work, and it's not very different from other technologies that have been used in other fields. If you look at signal processing, or how maybe the concept of signal processing anyway, it's been used in different applications. Brought in the audio wave, like for example, you're talking now, if someone is recording what you're talking and want to analyze what happened within the conference, what were the key areas, or if you look at also like the egg that is in electronics, something, you find such signals appearing. So the same concept also happened here with spectrometry, with cassava, and we're able to get such kind of information. So I will not go deep into the problem concept, but I also want to bring this talk close to the context of the conference about the techniques that are used in deep learning and etc. And what I found out during my research. So if you look at so we are still talking about diagnosis, disease detection using spectrometry. I'll be going back and forth. Yeah. So when you look at such a signal, and you think about what techniques do you want to use, for example, do we need to use to use this information, for example, to detect or to classify a disease. Yeah, so when we had this problem, we thought about different techniques to apply, different methods came in, different approaches came in, and also convolutional neural networks, which have been talked about in different tutorials previously by experts. So it was one way that we thought we could apply, but we're going to see what happened later and what we found out. So, CNN, as you can see, also with 1D, with spectrometry and signal processing, it's already like a one-dimensional array or a 1D. So what happens here is, you from such a simple architecture, you build your different convolutions, and then you add on, those are the layers, and then you add on whatever you want to add on later. So if you look at this paper, which I tried to cite, you see different applications of this kind of data that I had. So, which looks like this again, but eventually in the process of analysis and all that, we realized we had very many interests. What we wanted to find out on this spectral data. So if this is the spectral data that correlates to the diseases or the status of a cassava plant, so there are many things here someone would ask. Here we collected data on healthy plants for cassava. We also collected data on plants which are sick. and also which were sick with one disease and another disease. So someone would want to ask, do these spectral signals really, if you collected data as a spectral signal on a plant which is sick, does it look the same as a plant which is healthy, or do different classes differ? And so this was one of the processed signals which we had. And as you can see there, there's where the signal is really the same, where it moves slightly up, and etc. and etc. And also all this information we have, does it all relate to the disease, or do we have, or is that a particular area that is that is very interesting when we look at talk about the disease symptoms. So we found that one, again, to the application of this convolutional neural network, and okay, yeah, so we found that neural networks or convolutional neural network would not help us here. As you saw, as you heard from, I think even Samia talked about it here, I had her talk. She said usually once you feed in this data into a convolutional neural network, you, of course, you wait for the output, you again get the output. But we may not know where where the classifier learned features from. We don't get that from the output. I'm not a very big expert with CNN, but if someone has had that experience to say that if I fed in this data, I know my interesting features were here on this point, on this point, on these edges, particularly this, maybe they could also inform me. But that's what you could not find in convolutional neural networks. So we had to move further to explore with other classifiers or other techniques. And mostly importantly, I think we've also been introduced to matrices, and which was very, very good for these tutorials. So we wanted to learn these metrics, like given a spectrum. So how do we, which metrics or which features are more important for this spectrum of that related to the disease? So I think I'll be a bit faster. Oh, I think it's some time. Yeah. So before I introduce you the model or what we use, maybe I'll first show you what I mean if we have this signal, spectral signal that has been collected, and what is the matrix that you're trying to learn here. What does it mean? Maybe I'll first take you there, then I'll bring you back to here. Yeah, so this is the matrix we're talking about. So you saw our spectrum, which has features. Below is the wavelength from 400 to 900, which is really very, which we believe has enough information after removing the noise and all that. So if you look at here, our spectrum is being represented by this. So according to this algorithm, it ranks for us the features that it feels are more important after classification. So it returns these features for us. And when you look at that, so this is the matrix we're talking about, matrix learning. We are learning from the data we are giving a classifier, and after classification, it's going to tell us where it found features that are contributing to its accuracy in a way. I hope I'm clear. So how it works, so going back to the techniques or the algorithm itself, so we used LVQ, GMLVQ, which is a family of LVQ, and basically it works on prototypes. Yeah, so it works on prototypes. What you see there is you give it your features, you give it your label data, X new and Y new. Here they have the class, we have the feature, then also the class, which represents that. And it's like I said, it's a family of LVQ, which started like long time. There, if you try to read through the SOM techniques and all that, you'll see how it started. And initially, they used the Euclidean distance to measure the distance, for example, of your new input to the also the closest prototype, something like that. So, but with this kind of algorithm, it's more different from the first distance measures, yeah, which uses the quadratic approach. And I think you've seen our I think that is Professor Yurik. He was trying to explain many of these metrics or these algebra things, and I think this is not a very new thing to you here now. So, like I've said, this is a matrix that this is the future relevances that have been returned or that have been given to us after classification. And what you see there, the very top picks, was our area that was more relevant for this classification. We also had to learn more from these features, maybe which are low, and try to see are they really low? Do they contribute anything to this classification? And yeah, it's true they don't contribute much to the classification. You see the little bump here, and also maybe this could be like the noise at the end of the day. So like I've talked about the algorithm that it's based on prototypes. And so when you looked at our first signals that we gave a classifier, or these are the data points in short. So this data at the end of the day, it's clustered. Claire talked about clustering and all that and all that. And so when you look at how our prototypes, how our data is very moving towards these clusters. It was very amazing for us that we don't see this after the whole classification. We don't see this data all mixed up and all that. That would be weird, but you can also choose, you can also say maybe you need more than, if your data is not fitting well, you could say you choose more than one prototype, maybe two, uh, and etc. But I think 2-1 is already a very good thing to see your data fitting well. So more still on the prototypes that we want to learn them. So what is this that is important? That if you look at a healthy, if you look at a healthy plant, the signal from a healthy plant, does it relate to a signal to the diseased or something? So if you look at these prototypes, you realize, if you look at them keenly, you realize that they are more different, and in some areas maybe this is healthy, you see this is up, and we don't see something else looking like this here in this region, and also here, like that. So yeah, so that was also more interesting about the algorithm. It shows that we had to really understand how it was classifying and all that. So still, I think in the introduction, maybe I talked about, I'm close to finishing. Um, yeah, so here I talked about, we are talking about spectral data. So spectral data is very amazing, that it's very highly dimensional. You just look at a signal like this and you don't know how many features it has, but it has so many dimensions that if you're running it on your normal machine, actually I never ran anything on my machine because it was always like very heavy, working with over 1,000 data points or data points was really heavy for my machine. So the element of dimensionality reduction really comes in, that you can reduce these features from 3,600 features. You can reduce them, or they can be approximated using any of the reduction techniques. And we found PCA very interesting, that we can classify our data only using at least, I think we went with 30. If you see here, this is the accuracy. So by 30 data points, we already have the best 100% accuracy of to differentiate between the classes that we have given the algorithm or the classifier. So I also explained it with different types, which is not only PCA, but also wanted to know, because at the end of the day, we want to use this information for something else. We only don't want to stop at classifying. Wanted to know, what if we just, on this spectrum, we sampled a few elements, like maybe 10 points in an instance that you're maybe picking near infrared light on those few specific points that you have. So this how this peak selection came in, and also that method was able to give us some accuracy, some information that from the relevant areas, which was good for us to know. So yeah, so generally, like I can could conclude about the classification by showing this result that we tried out with different algorithm, different classifiers, say, and in original space, that means we have all the features, like I've said, which are very heavy or dimensional, highly dimensional. And CNN was really working well. Look at it, I think it's close to linear SVC. This is also not, it was third, and all that and all that. But when you look at in the low reduced space, so these classifiers start to behave in another way. So we saw geometric shooting up, and then we see SVC is still stable, like where it was, and then CNN's trying to play around, move down, and it is and it is. But when you look, when you go to, for example, the peak method, you can explain. I think people are the experts in CNN, why we have CNN working really below when we try to pick, when we try to point at to pick points on the spectrum. That means our signal is broken. And if you look at how convolutional neural network works, something has to be connected together. So which didn't work well for us here. I think that explains why we got just something very below average. So as I finish, so I've talked about a lot I think in a short time, but I need to finish for other presenters to talk, I think. So why are we doing all this? Why are we analyzing everything? Why are we looking into the details of something? And why not just feed our classifier and go and like, why not just get our data classified and feed it into any algorithm or classifier? But we went into the details to understand more uh, where where information is important, or which information is relevant. And at the end of the day, we are constructing this tool. So this tool, it cannot work on every information that we receive, or that is received from the light, or something like that. We have to be very specific with what we want to bring here, because we are looking at a low-cost tool, a low-cost resource. We also want to use low resources. So in terms of the architecture, but also on the data, so we have to give it data that is already filtered for it to work in a robust way. So this is where we are with our prototype. This is we could say it's our low-cost spectrometry tool. I didn't show the high-end spectrometer that gave us that data initially, but it's a very simple device, but very expensive. By looking at it, it's like a phone or something, but it's in thousands of dollars. So in thousands of dollars, it's not really applicable to use in our rural environment, or for the low smallholder farmers. So we are talking about this technology that that should be developed, that gives us the classification, tells us the disease of a plant at a very early stage. And how early? I think we're able to detect the disease from a cassava leaf as early as 10 weeks when the plant has been infected, or 10 to 12 weeks, yes. Yeah, that you can find it more in some of our work. I've not put in a lot of information, I think, to follow up here, but yeah. But if you're interested to know more about this work, then you can contact me, I think. Yeah, so thank you very much. I should be close to my minutes. Thank you.
Thank you so much, Dr. Godliver, for that perfect presentation. We are very happy that you've shown us that in as much as we learn all these hard mathematics and all this programming, it can be applied in Uganda. We're so grateful. Thank you so much.
Okay, thank you, Samia. Oh, okay,
So,
thank you for sharing that. Yes, thank you.
yeah, so according to the schedule, we are supposed to be going